This lecture is brought to you by Megger, a leading manufacturer of electrical test and measurement equipment. I've trusted Megger's equipment for years and have witnessed firsthand their commitment to education and supporting technical schools across the country. For a limited time, Megger is offering my viewers an exclusive discount on their next purchase on products sold through U.S. distributors. Simply visit us.megger.com/bigbadtech for all the details. Good day and welcome to Big Bad Tech. I'm instructor Jim Pytel, and today's topic of discussion is the rotating magnetic field. Our objective is to examine the rotating magnetic field common to a majority of three-phase AC motors and generators. We'll learn how two properties, the number of magnetic pole pairs per phase and excitation frequency, influence synchronous speed, and how swapping applied phase sequence determines rotational direction. Lastly, we'll learn to calculate slip. A disclaimer before we begin. During the course of this lecture, I'm going to use some very simple diagrams and make some large sweeping generalizations. Realize this is not a lecture on motor winding, and these diagrams are not meant to be taken as the literal truth. It'd be artistically impossible for me to accurately represent the sheer number and proper orientation of windings and poles within a reasonable amount of time, so these cave paintings will have to do. Let us begin. If we were to classify electrical machines, motors, and generators as taxonomous wood animals, the largest, sexiest, most important and powerful branch of the family tree would feature three-phase AC machines. The three-phase AC branch can be divided into two major genera, synchronous machines and induction machines. Each of these two genera can be further subdivided into two species. Three-phase AC synchronous machines could be classified as electrically excited synchronous machines or permanent magnet synchronous machines. And three-phase AC induction machines could be classified as squirrel cage induction machines or wound rotor induction machines. What differentiates these four related species from each other is largely the design of their rotor, i.e. the rotating business end that interacts with an applied load or prime mover. For the purposes of this introductory lecture, one can simply think of the rotor, regardless of origin, as one or more magnetic poles stuck to a shaft. We'll examine important differences and dirty details about these machines' performance characteristics, rotor design, operation, and more in later lectures. Today we'll focus on their commonalities. The unifying feature of these four three-phase AC species is the rotating magnetic field in the stator that powers their use. Three-phase AC, in addition to being easier to generate, transmit, transform, and use, innately creates a rotating magnetic field when applied to the stator, or stationary portion of a three-phase AC machine. In addition to creating a rotating magnetic field, by swapping any of the two applied phase sequences, the direction of the rotating magnetic field can be reversed. The term synchronous speed is the speed of the rotating magnetic field in units of revolutions per minute, or RPM. If you're seeking a superficial understanding of the rotating magnetic field and just want a quick method of determining synchronous speed, here's a formula often used to calculate it, where synchronous speed is 60 times the excitation frequency divided by the number of pole pairs per phase used to construct the stator field. Key to the correct interpretation of this formula is properly distinguishing between the terms poles, poles per phase, and pole pairs per phase. These similarly sounding terms most assuredly do not mean the same thing. You'd think motor manufacturers would adopt a single standard, but they haven't, and it's often up to you to decipher what term a particular datasheet is employing. A pole is a point on a magnet which lines of magnetic force are directed from or to. Consider a simple bar magnet. This magnet has a north pole from which lines of magnetic force emanate and a south pole from which magnetic lines of force are directed to. This is a two-pole magnet. Now, to differentiate between the term pole and pole pair, perform this simple task. Walk into your local magnet store, saunter up to the counter, and tell the clerk you wish to purchase a single pole. North or south, it doesn't matter. You just want a magnetic monopole without anything else attached. Most likely, the clerk will roll their eyes, sigh heavily, and call their manager, if not security. There is no such thing as a pole. Magnetic poles always appear in pairs. This two-pole magnet is a single pole pair. Poles always occur in pairs, and only in relation to one another is there a north and south pole pair. Quite like yin and yang, one is not all one at the exclusion of the other. Unfortunately, not all manufacturers have reached the same level of enlightenment, and you may or may not see these terms used correctly, and maddeningly enough, interchangeably, as if they are equivalent. They are not equivalent. They never will be equivalent. 2 poles make a single pole pair. 4 poles make 2 pole pairs. 6 poles make 3 pole pairs, and so on. The number of poles is always twice the number of pole pairs, and the number of pole pairs is always half the number of poles. Really, the hard part is often deciphering what definition a particular individual, textbook, manufacturer, or datasheet might be utilizing. Add to this confusion the fact that 3-phase AC machines, as implied by their titles, are powered by 3-phase AC. Regardless of the term employed, pole or pole pair, 1/3 of the total number is intended for use with phase L1, another 1/3 for phase L2, and the remaining third for phase L3. This yields the following relationship. See if you can follow this logic. A circular stator consists of a total number of poles. This total number of poles divided by 3 is the number of poles per phase, and the number of poles per phase divided by 2 is the number of pole pairs per phase. Consider a 3-phase AC stator winding consisting of 6 individual poles. This also directly implies that there are 2 poles per phase and a single pole pair per phase. Similarly, consider a 3-phase AC stator winding consisting of 12 individual poles. This also directly implies there are 4 poles per phase and 2 pole pairs per phase. Similarly, consider a 3-phase AC stator winding consisting of 18 individual poles. This also directly implies there are 6 poles per phase and 3 pole pairs per phase. I could keep going, but you get the picture. There is a defined relationship between the term poles, poles per phase, and pole pairs per phase, and these terms are not equivalent with one another, nor can they be used interchangeably. Now that we've clearly defined these terms, let's try a couple simple examples of the synchronous speed formula. Consider a stator with 6 total poles, 2 poles per phase, or a single pole pair per phase, operated at 60 Hz. An application of the synchronous speed formula demonstrates the speed of the rotating magnetic field produced by the stator revolves at 3,600 revolutions per minute. Now, what if we box this motor up, shipped it across the ocean, and installed it in some Belgian chocolate factory using a 50 Hz AC system commonly available in the EU? Another application of the synchronous speed formula demonstrates the speed of the rotating magnetic field produced by the stator now revolves at a slower 3,000 RPM when operated at a slower frequency of 50 Hz. This example illustrates that excitation frequency directly influences synchronous speed. Decreased frequency and synchronous speed decreases. Conversely, increased frequency and synchronous speed increases. Let's now examine how the number of poles, poles per phase, or pole pairs per phase influences synchronous speed. Consider the following selection of motors with the indicated number of pole pairs per phase, all operated at 60 Hz. As previously, a single pole pair per phase motor operated at 60 Hz has a synchronous speed of 3,600 RPM. The second motor, with twice the number of pole pairs per phase also operated at 60 Hz, has a synchronous speed of 1,800 RPM. The third motor, with 3 times the number of pole pairs per phase as the first, also operated at 60 Hz, has a synchronous speed of 1,200 RPM. Finally, the last motor with a crapload of pole pairs per phase, operated at 60 Hz, has a synchronous speed of 75 RPM. These examples illustrate an important fact, that fact being the number of pole pairs per phase inversely influences synchronous speed. Decrease the number of pole pairs per phase, and synchronous speed increases. Conversely, increase the number of pole pairs per phase, and synchronous speed decreases. This may initially go against the more is better instinct most of us have, but it's true, as I'll laboriously demonstrate in a moment. More pole pairs per phase result in a slower synchronous speed, and less pole pairs per phase result in a faster synchronous speed. This synchronous speed formula tells us there are 2 ways to vary motor speed: frequency and pole pairs. Motor construction, i.e. the number of pole pairs per phase, if you think about it, is a primitive form of speed control, even with fixed frequency systems. Want a faster system? Buy a motor with less pole pairs per phase. Want a slower system? Buy a motor with more pole pairs per phase. This being said, controlling speed via the number of pole pairs per phase doesn't nearly offer the degree of fine control one has by varying excitation frequency. You note in fixed frequency systems, you're left with discrete levels of speed, almost like quantum states, with huge dead bands in between, 3600 to 1800, 1800 to 1200, and so on. If you wanted 2400 RPM in the no man's land between a single pole pair per phase and 2 pole pair per phase motors, you'd be out of luck, unless you used a gearbox with an appropriate step-up or step-down ratio. Either a single pole pair per phase motor with a 1.5 to 1 step-down gearbox, a 2 pole pair per phase motor with a 1 to 1.3 step-up gearbox, a 3 pole pair per phase motor with a 1 to 2 step-up gearbox, or other combinations would do the trick. Even if you did figure out the appropriate motor and gearbox ratio, you'd be stuck at or around 2,400 RPM with very little room for maneuverability. For this reason, a power electronics device known as a motor drive is becoming the preferred means of speed control for most applications. A motor drive varies the voltage, magnitude, and excitation frequency delivered to a motor under its direction, thus directly controlling that motor's speed. Slower excitation frequency, slower motor. Higher excitation frequency, faster motor. Again, consider a 2 pole pair per phase motor being employed in an application that necessitates a synchronous speed of 2,400 RPM. Ordinarily, if driven by a fixed frequency system at 60 Hz, this motor would have a synchronous speed of 1,800 RPM. If, however, we used a motor drive that could vary the excitation frequency, we could drive this motor at an increased speed. What frequency does this motor drive need to produce to generate 2,400 RPM synchronous speed? In short, we know synchronous speed, we know the number of pole pairs per phase, we need to solve for frequency. An algebraic manipulation of the synchronous speed formula, solved for unknown frequency, demonstrates that frequency is the synchronous speed times the number of pole pairs per phase divided by 60. Substituting our given values demonstrates this motor needs to be driven at an increased 80 Hz. In addition to allowing this fine degree of customization, a motor drive additionally offers acceleration and deceleration control and other advanced features, all without the necessity of a clunky, greasy, noisy gearbox. Like I said, we'll examine motor drives and more in later lectures. While we're still discussing the synchronous speed formula, the observant among you may have noticed a pattern regarding pole pairs per phase and synchronous speed. Motors with a single pole pair per phase have a synchronous speed of 3,600 RPM. Think of 3,600 RPM as the base speed established by a 60 Hz system. You recall 60 Hz means 60 cycles per second. What if you stood there for a full minute? 1 minute is 60 seconds. 60 cycles per second times 60 seconds per minute yields 3,600 RPM. Motors with 2 pole pairs per phase have a synchronous speed of half of 3,600 RPM or 1,800 RPM. Motors with 3 pole pairs per phase have a synchronous speed of 1/3 of 3,600 RPM or 1,200 RPM. If we continue this fashion, we'd find that motors with 4 pole pairs per phase have a synchronous speed of 1/4 of 3,600 RPM or 900 RPM, and so on. You'll note in our previous examples, 75 RPM is 1/48th of 3,600 RPM. If we operated these same motors at 50 Hz, we'd observe a similar pattern. Motors with a single pole pair per phase have a synchronous speed of 3,000 RPM at 50 Hz. This is what you would observe if you stared at a 50 Hz system for 1 full minute. 50 cycles per second times 60 seconds per minute yields 3,000 revolutions per minute. This is the base speed for a 50 Hz system. Motors with 2 pole pairs per phase have a synchronous speed of half of 3,000 or 1,500 RPM. Motors with 3 pole pairs per phase have a synchronous speed of 1/3 of 3,000 or 1,000 RPM. If we continue this fashion, we'd find that motors with 4 pole pairs per phase have a synchronous speed of 1/4 of 3,000 or 750 RPM, and so on. If you work with these systems long enough, you'll recognize these types of patterns. Moving on. Now that we've got a general idea of how the properties frequency and the number of pole pairs per phase influence synchronous speed, let's examine an iterative step-by-step illustration of the rotating magnetic field produced in a 3-phase AC stator. Operationally, one might think of a pole pair as an angular stopping point on the way around a full 360-degree circle. Allow me to demonstrate. Consider a 3-phase AC stator winding consisting of 6 individual poles, 2 of which are energized by phase L1, 2 of which are energized by phase L2, and 2 of which are energized by phase L3. This 6-pole stator has 2 poles per phase. Given poles never appear in isolation, but only with their opposite in tow, it can also be said that this is a single pole pair per phase motor. I've illustrated each winding forming a pole pair as having 2 ends, A and A prime, B and B prime, and C and C prime. These windings can be wired in Y or delta, it doesn't really matter. All that matters is they are energized by 3 sinusoidal voltage waveforms, 120 degrees out of phase with one another. Let's assume the motor is wound such that the A, B, and C ends all achieve north magnetic polarity, and the associated A', B', and C' ends all achieve magnetic south polarity when their associated phases achieve maximum positive polarity. Whereas, when their associated phases achieve maximum negative polarity, let's assume this motor is wound such that the A, B, and C ends are souths, and the associated prime ends are norths. I say again, let's assume that this motor is wound such that when the associated voltage phase achieves maximum positive polarity, the A, B, and C ends are norths, and the associated prime ends are south. Whereas, when the associated phase achieves maximum negative voltage polarity, let's assume the opposite, i.e. the A, B, and C ends are souths, and associated prime ends are norths. By the way, this is a cartoonish simplification, but gets the necessary point across without too much difficulty. Winding A' is presently energized by phase L1 in black. Winding B' is presently energized by phase L2 in red. Winding C' is presently energized by phase L3 in blue. We started our analysis with the rotor in the present position at time t equals 0. Ultimately, norths on the rotor will be attracted to the souths on the stator, and the souths on the rotor will be attracted to norths on the stator. Ideally, we should see the stator establish a rotating magnetic field such that the rotor is dragged in a full circle. With 6 total poles, we have effectively divided this full circle into 1/6 of 360, or 60-degree angular increments. The first interesting thing happens when L2 peaks negatively. B becomes the south. B' is a north. The north end of the rotor is attracted to B, and the south end of the rotor is attracted to B'. The motor turns clockwise. Some moments later, L1 peaks positively. A is a north, and A' is a south. The north end of the rotor is attracted to A', and the south end of the rotor is attracted to A. The rotor continues to turn clockwise. Some moments later, L3 peaks negatively. C is a south, and C' is a north. The north end of the rotor is attracted to C, and the south end of the rotor is attracted to C'. The rotor continues to turn clockwise. Some moments later, L2 peaks positively. B is a north, and B' is a south. The north end of the rotor is attracted to B', and the south end of the rotor is attracted to B. The rotor continues to turn clockwise. Some moments later, L1 peaks negatively. A is a south, and A' is a north. The north end of the rotor is attracted to A, and the south end of the rotor is attracted to A'. The rotor continues to turn clockwise. Finally, some moments later, L3 peaks positively. C is a north, and C' is a south. The north end of the rotor is attracted to C', and the south end of the rotor is attracted to C. The rotor continues to turn clockwise. We're right back where we started, having completed a full 360-degree revolution. Importantly, we completed this full physical revolution in one cycle of sinusoidal AC. Operated at 60 cycles per second, this means a full revolution takes 1/60, or 16.7 milliseconds. If we stood here for 1 full minute, or 60 seconds, we'd observe 60 seconds divided by 16.7 milliseconds per revolution, or 3,600 RPM. Can you dig it? A single pole pair per phase stator produces a rotating magnetic field that necessitates one complete cycle of sinusoidal AC to complete a full revolution. If you think about it, a single pole pair per phase motor has 6 check-ins along the way. Technically 3 because they always occur in pairs, but I'm counting them as 6 because each end can assume north or south polarity, depending upon voltage polarity, and there's 6 total positive and negative peaks in a full cycle 3-phase AC. L2 negative, L1 positive, L3 negative, L2 positive, L1 negative, and L3 positive. Let's now examine how phase sequence determines rotational direction. You notice previously connected, L1 to A, L2 to B, and L3 to C, the rotating magnetic field revolves in the clockwise direction. 3-phase AC, in addition to establishing a rotating magnetic field, makes it supremely easy to change rotational direction by swapping any 2 phases. Allow me to demonstrate. Consider this subtle modification its profound impact. Winding A remains energized by phase L1 in black. L2 and L3, however, swap seats on the bus. Winding B is now energized by phase L3 in blue, and winding C is now energized by phase L2 in red. Let's start this analysis with the rotor in this present position at time t equals 0. Ideally, we should still see the stator establish a rotating magnetic field only this time in the opposite direction. The first interesting thing happens when L2 peaks negatively. C is the south, C' is the north. The north end of the rotor is attracted to C, and the south end of the rotor is attracted to C'. The motor turns counterclockwise. Some moments later, L1 peaks positively. A is the north and A' is the south. The north end of the rotor is attracted to A', and the south end of the rotor is attracted to A. The rotor continues to turn counterclockwise. Some moments later, L3 peaks negatively. B is the south and B' is the north. The north end of the rotor is attracted to B, and the south end of the rotor is attracted to B'. The rotor continues to turn counterclockwise. Some moments later, L2 peaks positively. C is the north and C' is the south. The north end of the rotor is attracted to C', and the south end of the rotor is attracted to C. The rotor continues to turn counterclockwise. Some moments later, L1 peaks negatively. A is the south and A' is the north. The north end of the rotor is attracted to A, and the south end of the rotor is attracted to A'. The rotor continues to turn counterclockwise. Finally, some moments later, L3 peaks positively. B is the north and B' is the south. The north end of the rotor is attracted to B', and the south end of the rotor is attracted to B. The rotor continues to turn counterclockwise. We're right back where we started, having completed a full 360-degree revolution, only this time in the opposite direction. Swapping two phase sequences resulted in the complete reversal of the rotating magnetic field. This method is often used in reversing motor starters, a type of bidirectional motor control circuit where a given phase sequence establishes forward operation and a different phase sequence establishes reverse operation. We'll examine reversing motor starters in later lectures in motor control. What's beautiful about this feature is that swapping any two phase sequence results in a complete reversal of the rotating magnetic field, regardless of choice. Customarily, one swaps L1 with L2. However, as we demonstrated, swapping L2 with L3 works equally as well. For the doubtful among you, given the present configuration, I invite you to swap any two phase sequences with one another and perform the same iterative analysis. Seriously, swap any two phases and it will reverse. L1 with L2, L2 with L3, or L3 with L1. Regardless of the choice you make, so long as you only swap two, you should see the field return to clockwise rotation. Alright, let's do the same type of iterative analysis for a three-phase AC stator consisting of 12 poles, 4 poles per phase, or 2 pole pairs per phase. Windings A1 and A2 are energized by phase L1 in black. Windings B1 and B2 are energized by phase L2 in red. Finally, windings C1 and C2 are energized by phase L3 in blue. We start our analysis with the rotor in the present position at time t equals 0. Ultimately, the norths on the rotor will be attracted to the souths on the stator, and the souths on the stator will be attracted to norths on the stator. Ideally, we should see the stator establish a rotating magnetic field, just as the rotor is dragged in a full circle. With 12 total poles, we've effectively divided this full circle into 1/12 of 360 degrees, or 30-degree angular increments. The first interesting thing happens when L2 peaks negatively. B1 and B2 are souths, and the prime ends are norths. The rotor turns clockwise. Some moments later, L1 peaks positively. A1 and A2 are norths, and the prime ends are souths. The north ends of the rotor are attracted to the A' ends. The south ends of the rotor are attracted to the A's. The rotor continues to turn clockwise. Some moments later, L3 peaks negatively. The C ends are south, and the prime ends are norths. The north ends of the rotor are attracted to the C's, and the south ends of the rotor are attracted to the primes. The rotor continues to turn clockwise. Some moments later, L2 peaks positively. The B ends are norths, and the prime ends are souths. The north ends of the rotor are attracted to the primes, and the south ends of the rotor are attracted to the B's. The rotor continues to turn clockwise. Some moments later, L1 peaks negatively. The A ends are south, and the prime ends are norths. The north ends of the rotor are attracted to the A's, and the south ends of the rotor are attracted to the primes. The motor continues to turn clockwise. Some moments later, L3 peaks positively. The C ends are north, and the prime ends are souths. The north ends of the rotor are attracted to the primes, and the south ends of the rotor are attracted to the C's. The rotor continues to turn clockwise. After one full cycle of three-phase AC, we've completed half a full rotation, or 180 degrees. You can see where I'm going with this. The next full cycle should bring the rotor the remaining 180 degrees. L2 again peaks negatively. The B ends are souths, and the prime ends are north. The north ends of the rotor are attracted to the B's, and the south ends of the rotor are attracted to the primes. The rotor turns clockwise. Some moments later, L1 peaks positively. The A ends are norths, and the prime ends are souths. The north ends of the rotor are attracted to the primes, and the south ends of the rotor are attracted to the A's. The rotor continues to turn clockwise. Some moments later, L3 peaks negatively. The C ends are souths, and the prime ends are norths. The north ends of the rotor are attracted to the C's, and the south ends of the rotor are attracted to the primes. The rotor continues to turn clockwise. Some moments later, L2 peaks positively. The B ends are norths, and the prime ends are souths. The north ends of the rotor are attracted to the primes, and the south ends of the rotor are attracted to the B's. The rotor continues to turn clockwise. Some moments later, L1 peaks negatively. The A ends are souths, and the prime ends are norths. The north ends of the rotor are attracted to the A's, and the south ends of the rotor are attracted to the A primes. The rotor continues to turn clockwise. Some moments later, L3 peaks positively. The C ends are norths, and the prime ends are souths. The north ends of the rotor are attracted to the C primes, and the south ends of the rotor are attracted to the C's. The rotor continues to turn clockwise. We're right back where we started, having traveled full 360 degrees over the course of 2 cycles of sinusoidal AC. Operated at 60 Hz, this means a full revolution takes 2 times 16.7 milliseconds, or roughly 33.3 milliseconds. If we stood here for a full minute, or 60 seconds, we'd observe 60 seconds divided by 3.3 milliseconds per revolution, or 1800 RPM. Can you dig it? The 2-pole pair per phase stator has a slower synchronous speed because it's got twice as many stops to make. It's kind of like a Mexican public bus that rather than stopping at a limited number of central bus stations, it stops at each and every single person's house in the entire city. Ask me how I know. As tedious as this iterative step-by-step analysis may have been, it's comforting to realize that it confirms the results we obtained earlier using the synchronous speed formula. While we got this diagram in front of us, for the curious among you, I invite you to swap the applied phase sequence to any 2 sets of windings and perform the same step-by-step analysis again. For example, let's say L1 and L2 switch seats in the bus, such that the A windings are now energized by phase L2 in red, the B windings are now energized by phase L1 in black, and the C windings remain energized by phase L3 in blue. Ideally, you should see the same behavior, only in the opposite or counterclockwise direction. Again, swapping any 2 phases in a 3-phase AC stator results in the reversal of the rotating magnetic field. Note as I've clumsily illustrated this phenomenon in the past couple examples, one might get the mistaken impression that the rotor moves in jerky, stepwise increments. This isn't really true. As current through a particular winding sinusoidally peaks and valleys, the associated magnetic field sinusoidally varies in intensity and polarity. In addition, real stator windings actually feature a bit of physical overlap between adjacent poles, such ultimately that the rotating magnetic field revolves around the stator seamless as a bunch of football fans doing a wave around a stadium. Here's a clip from the Wikipedia entry about 3-phase AC motors that I never get tired of watching. The rotating magnetic field, because of the contributions of 3 120-degree offset waveforms and physically overlapped windings, actually appears with a relatively constant intensity, smoothly revolving around the stator. The observant among you may notice something interesting about the relationship of the stator and the rotor speed. I'll return to this clip at the end of this lecture to explain this phenomenon. Alright, now let's relate the rotating magnetic field with our previous understanding of mechanical power by comparing and contrasting a single pole pair per phase stator with that of a 2-pole pair per phase stator. Let's assume these 2 machines have the same power rating. For the purposes of argument, let's say they're both 200-watt machines. As we've demonstrated, a single pole pair per phase stator necessitates a single cycle of AC to perform a complete physical revolution, whereas a 2-pole pair per phase stator necessitates 2 cycles of AC to perform a complete physical revolution. Operated at 60 Hz, the single pole pair per phase stator would have a synchronous speed of 3600 RPM, whereas the 2-pole pair per phase stator would have a synchronous speed of 1800 RPM. The motor with a smaller number of pole pairs rotates faster because it's got less stops to make. The motor with a greater number of pole pairs per phase rotates slower because it's got more stops to make. Additionally, as this diagram is intended to illustrate, The two-pole pair per phase stator is slightly physically larger than the single-pole pair per phase stator, simply because it needs more room to accommodate a larger number of poles. You'll recall from the rotating mechanical power lecture, available at the Big Bad Tech channel, that rotating mechanical power in watts is the product of torque in units of Newton meters times rotational speed in units of RPM divided by the constant 9.55. Given your understanding of rotating mechanical power, can you explain how and why the number of pole pairs per phase influences torque? We know each motor's rated power, in both cases 200 watts. We additionally know the synchronous speed for each motor. We need to solve for torque. An algebraic manipulation of the mechanical power formula solved for torque demonstrates that torque is power times 9.55 divided by speed. Substituting in our given values demonstrates the single pole pair per phase motor generates 0.53 Newton meters of torque, whereas the similarly rated two-pole pair per phase stator generates 1.06 Newton meters, or twice as much torque. The math is pretty clear. If these truly are both similarly rated 200-watt motors, the calculations demonstrate the two-pole pair per phase motor generates twice as much torque because it's going at half the speed. The reasons are pretty obvious when you look at the diagrams. The single pole pair per phase motor has half as many magnets generating torque, whereas the two-pole pair per phase motor has twice as many magnets generating torque. For similarly rated motors, there's a trade-off between speed and torque because there's a trade-off between the speed of the rotating magnetic field and the combined strength of the magnetic poles forming the field. Alright, the last topic I wanted to discuss is slip. The observant among you may have noticed an interesting feature in the clip I previously displayed. If it escaped your attention earlier, let me point it out to you now. You will note that there is a slight differential between the speed of the rotating magnetic field produced by the stator and the rotational speed of the rotor. The stator rotating magnetic field is ever so slightly faster than the rotational speed of the rotor, such that the stator regularly catches up, passes, and overlaps the rotor. This is not an artifact in the video clip, but rather a real observable fact for certain types of three-phase AC motors. This property is known as slip, the degree of differential between the stator and the rotor speed. As we'll learn in later lectures, different types of motors and generators have different operational characteristics depending upon construction. One of the key differences observed between synchronous and induction split in the three-phase AC family tree is with regard to slip. The rotors of synchronous machines, as implied by their titles, are synchronized with or match the synchronous speed of the stator, whereas induction machines exhibit a degree of differential between the rotor and synchronous speed. This implies that synchronous machines are ideally constant speed machines, whereas induction machines exhibit variable speeds as a function of applied load. The more load, the more slip. The rotors of induction machines always slightly lag or are slightly slower than the synchronous speed of the stator rotating magnetic field, even in the unloaded state. For this reason, induction machines are sometimes referred to as asynchronous, meaning not synchronized. This degree of lag is called slip and is typically expressed as a percentage of synchronous speed. Slip is the difference between the rotational speed of the rotor and the synchronous speed over a synchronous speed times 100%. Consider a two-pole pair per phase squirrel cage induction motor operated at 60 Hz with a synchronous speed of 1800 RPM. In the unloaded condition, when it's producing no torque, let's say the motor turns at 1780 RPM. The rotor lags synchronous speed by 20 RPM, where 20 RPM is roughly 1.1% of synchronous speed. If we load this motor up to its rated condition, such that it's producing its rated power or rated torque, let's say the rotor slows down to the rated speed of 1692 RPM. The rotor lags synchronous speed by 108 RPM, where 108 RPM is 6% of synchronous speed. A similar phenomenon is observed with induction generators, only in the opposite direction. In order to export real electrical power, a prime mover must exert sufficient torque to drive the rotor faster than synchronous speed. Consider a modern horizontal axis wind turbine generator featuring 3 pole pairs per phase and a 60 Hz AC system. The natural synchronous speed of the stator will be 1200 RPM. Let's say the motor, however, is being driven at 5% leading slip via the main shaft and step-up gearbox intermediary. 5% of 1200 RPM is 60 RPM. This means the rotor is turning at 1260 RPM, or 5% faster than synchronous speed. Alright, that is that. I do believe we covered what I intended to and more. In conclusion, this lecture presented the rotating magnetic field common to three-phase AC machines, motors, and generators. We define the term synchronous speed and examine those properties that influence. Additionally, we demonstrated that swapping any two applied phase sequences results in complete reversal of the rotating magnetic field. Finally, we defined and learned to calculate slip. Remember to review this material as often as you need to really drive it home. Imagine how well lab will go if you know what you're doing. Thank you very much for your attention and interest, and we'll see you again during the next lecture of our series. Remember to tell your lazy lab partner about this resource, and be sure to check out the Big Bad Tech channel for additional resources and updates.